Last week we defined the space H1P as the completion of C-infinity functions under the Sobolev norm. That definition is very convenient, and using some simple functional analysis we were able to show that to every function in here we could associate an LP function and an LP vector valued function, which we could call gradient of U. The alternative definition of Sobolev spaces, where you directly introduce some object as the derivative, is through weak derivatives, and the resulting space will be called W1P. So today we want to talk about this one and the brilliant theorem due to Meyers and Serrin that indeed the two spaces end up being the same. Maybe one of the most important theorems in Sobolev theory. The setting will always be that we have the Lebesgue measure, unlike last week. Openness condition is required so that we can talk about the smooth functions. We can talk about the smooth functions on non-open sets, but that is a technicality in its own. We introduce weak derivative for measurable functions in L1 log of your omega. The reason for that is so that this integral is well defined and is a finite number. These requirements are the minimal to even talk about this. You need openness of the domain, and you need these functions to be locally integrable. We call a function Vj, a measurable locally integrable function, a weak derivative, a weak partial derivative of u in the jth direction if this integral equality holds for every compactly supported function in omega. If u happens to be a C-infinity function itself, then partial with respect to jth coordinate will be actually satisfying these conditions. Such Vj is unique as a measurable function, so on a set up to redefining on null sets. So we shall write that Vj is partial with respect to jth coordinate of u, so that this now notation is justified. W1p of omega is the collection of all functions in L1 log, so that all partials, weak partials, exist, and u belongs to LP, that is the role of LP, and all these partials also belong to LP of omega. A very important distinction here, extremely important, is that this condition for differentiability includes no reference to P. So W1P space is differentiability, which has no P in it, plus a simple integrability requirement. With simple, I mean a separate integrability requirement on the function and its weak partials. So in some sense, you see that the role of P in this definition is not too intrinsic, at least from the definitions. C-infinity functions of omega belong to W1P, except there is a technicality, because if omega is an unbounded domain, for instance, this may not be integrable. Take even a constant function. So you can say with finite W1P norm. We didn't define it, but W1P norm, we can just guess what it is. So this will be LP norm of the function plus LP norm of all of its partials. So as long as the C-infinity function has the integrability requirement on itself and its derivatives, this will be in W1P. This one is the smallest Banach space containing this set. By its definition, it's the closure. So consequence of this lemma, H1P of omega is a subset of W1P of omega. And that's where this beautiful theorem of Meyers and Serrin comes in. H equal W, and the paper itself is only 2 pages long. As they explain here, we observe that H is subset W by very definitions. Conversely, Friedrichs proved that locally a weak derivative is strong. The belief persists, however, that in the large this is not the case. Authors using the subspaces H and W will often distinguish between them and point out that they are the same, provided that the boundary of omega satisfies certain smoothness conditions. Here, in this paper they mean, we shall show that they are always the same. Theorem H equal W. Let me also quote something from Wikipedia, which also quotes it from a book by Adams and Fournier. This result, published in 1964 by Meyers and Serrin, ended much confusion about the relationship of these spaces that existed in the literature before that time. It is surprising that this elementary result, of course everything after being proved is elementary, right? That this elementary result remained undiscovered for so long. So in modern textbooks, this is probably first or second theorem that they prove about Sobolev spaces, and it gives the impression rather that it is really simple or elementary, but if it took some time to discover, that means it wasn't that obvious. Another feature of this theorem is that the result does not require any smoothness of the domain, unlike many density theorems. Actually, there is a version where you want to prove that C infinity functions up to the boundary, that means C infinity on the closure of the boundary, which has to be defined precisely, to prove that that space is dense in this Sobolev spaces. That does need some assumptions on the boundary of the set. There's also a historically intriguing thing here. They say that now that we know these are equal, we are of the opinion that the phrase strong derivative is the appropriate terminology to retain, following the present practice of most mathematicians. So because they call the derivatives of H functions strong, and therefore here they showed that W is not really a bigger space, so there's no need for weaker notion. And from that point of view, they are right that they should be called strong derivatives, but history was different, and as I just defined and is the common notation, we call these derivatives in sense of partial integration by parts weak derivatives. And that is the modern terminology. With one definition, some property is immediate, and with some other properties are immediate. For instance, the reason why Sobolev spaces are Banach, that they are closed, there is nothing to prove if we use H, because it's defined as a completion, but with W it's different. Let me give you another example. You are a W11 function, and it happens that U is in LP, in fact, and gradient of U is in LP. That means each individual weak partial derivative is there. Then U is in W1P of omega. This is immediate because of definition. As I said, weak derivative here is the same as for W1P. So weak derivative for W1P and W11 is the same condition. Prove the same for H1P class, H11 versus H1P, without using H equal W